Introductory computer science courses typically frame binary search as a specific, linear querying tool. Most engineers rely on a literal mental model. You are given a static list of sorted integers and must pinpoint the exact location of a single target number. This process relies on repeatedly dividing an ordered dataset in half, shrinking the physical bounds until the target is isolated. If we dissolve the literal numbers, the underlying logic remains. The mechanism driving those divisions ignores the specific data type. It only requires that the states remain in a predictable order. This reliance on explicit arrays becomes a liability when developers encounter optimization problems that lack a pre-computed list of values. Binary search functions as a generalized optimization framework, navigating any state space governed by a monotonic feasibility function. Discarding the array illusion allows for solving complex algorithmic constraints in O log n time. To understand this generalized search, we must look past programming syntax to the mathematical principles dictating the search space. The defining constraint is monotonicity, a relationship where the function travels in only one direction, staying exclusively non-decreasing or non-increasing. This 2D plot shows a non-decreasing line, representing predictable growth that never reverses. It follows a strict rule. If x1 is greater than x2, f of x1 must be greater than or equal to f of x2. A sorted array snaps into place along this continuous curve. As the index increases, the value predictably increases or remains static, satisfying the definition of a monotonic function. Because sorted lists behave like these curves, we can apply binary search to any mathematical function that shares this non-decreasing signature. We can simplify this further by restricting the function to output only Boolean values, true or false. By applying a threshold rule, like x being greater than or equal to 10, our integer array converts directly into a sequential Boolean output. This creates a stark boundary between states that fail the condition and those that meet it. Once the condition evaluates to true, the rules of monotonicity dictate that all subsequent larger states must also be true. The mechanical objective centers on identifying the exact edge of that transformation, the very first true in a sorted Boolean sequence. Any algorithmic problem that maps to this false to true pattern is guaranteed to be solvable via binary search. Consider the Koko's bananas problem, where we must find the minimum speed required to finish a task within a strict time limit. Instead of searching static numbers, we are evaluating a physical rate of execution that is constantly increasing, acting like an engine pushing to absolute limits. The constraint is to find the absolute minimum speed k that satisfies the time limit. Since potential speeds stretch toward infinity, we cannot pre-compute an array of every possible answer. We instead visualize an infinite axis for the variable k. Testing slower speeds reveals they fail the time constraint, populating the left side with false results. Once speed reaches an adequate rate, the function returns positive results, completing the false to true pattern. If a specific speed k completes the task, every speed greater than k must also complete it. This removes the need for a physical array. We only need to evaluate the specific speed k that the binary search guesses in the moment. Infinite optimization problems are simply Boolean boundary searches, which neutralizes the difficulty of infinite search spaces. This logic maps directly to a standardized software engineering template. This code represents the raw anatomy of the generalized binary search. The midpoint calculation provides the initial guess within our theoretical state space. The evaluation function acts as a black box. The search loop only requires that this line returns a binary true or false. The search loop ignores the internal complexity of the problem, focusing only on the Boolean output. If the function returns true, the algorithm logs the current guess and shifts the right boundary down. Logging the value stores a valid answer, while shifting the boundary forces the search to continue further to the left. This leftward pressure ensures we find the absolute edge of the monotonic boundary, rather than a random valid state. If the guess is false, the boundary shrinks to the right, discarding all lesser values instantly. This template decouples the O of log n mechanical search from the specific constraints of the problem. This approach changes how we tackle complex algorithmic questions. Optimization becomes a matter of logic mapping. You stop writing custom search algorithms from scratch and instead define the rules of the search space. The search template on the left remains static. Your engineering effort is focused on the feasibility function on the right, where you define the problem's unique constraints. If those constraints map to a monotonic sequence, the static template will resolve the problem perfectly. This abstraction provides O log n efficiency, regardless of the nature of the task. When facing an intimidating optimization question, your first step is to build the logic that tests a single guess. Solving complex optimizations requires identifying the monotonic boundary that makes the solution inevitable.